Hi everyone, welcome to your notes on section 10.1. Today we are going to start into the world of circles. So let's get into different properties of tangents. Now we've talked about tangent before in right triangle trigonometry. So this could be a bit confusing, but we're going to be using tangent in a whole different context when we're talking about circles. So we're not talking about the trig ratio of opposite over adjacent. Now when we're talking about tangent, we're talking about a line. So first and foremost, what is a circle? A circle is the set of all points in a plane that are equidistant. Yeah, that's just a fancy word for equal distance from a given point. So on your circle, on your notes, we're going to do some labeling. In the middle of your circle is called your center. So that's that point that is equal distance to all the points on the circle, right? We have the line that goes from one end to the other that crosses through the center. That's known as the diameter. The radius is the line that goes from the center to any endpoint on the circle. A chord is a line segment within the circle that has an endpoint on both endpoints are on the circle. So technically the diameter is a chord, but a chord could be something other than the diameter. So here are the actual word definitions. So a chord is a segment whose endpoints are on a circle. Again, pause this video as you need it. I'm going to keep plugging through, assuming that you're going to do that. A secant is a line that intersects a circle in 2 points. So notice the difference. A chord is a segment. A secant is a line. Remember, lines go on and on and on forever. A segment doesn't. It has endpoints. A tangent is a line in the plane of a circle that intersects the circle in exactly 1 point. And that point where it intersects, we call the point of tangency. Okay, so let's go ahead and do a few examples and see if we can identify all of these. So for our first one, there we go, here's our first one. We need to tell whether the line, ray, or segment is best described as a radius, a chord, diameter, secant, or tangent. Okay, so notice the symbol above the letters DC. There are no arrows on it. So that means we are talking about a segment. So out of my options, my only things that it could potentially be are a radius, a chord, a diameter. It can't be a secant, right? Can't be a secant because a secant has to be a line. It could technically, I guess, be a tangent if it's outside. So let's go find point D. Point D is down here and C is right here. So doesn't go all the way through the circle. So its endpoints are not on both sides of the circle. So it can't be a chord, it can't be a diameter. So and it's inside, so it can't be a tangent. Tangent needs to be outside of the circle. So my only option is a radius. And yes, it is a radius because it has an endpoint on the circle and its other endpoint is in the center of the circle. B, DE. Again, we have the same situation. It can't be a secant because the secant has to be a line. If I look at D and E, those are both points on the side of the circle, so it can't be a radius. So now I'm down to either chord or diameter. Can't be a tangent because the tangent is outside. So is it a chord? Is it a diameter? Well, this one goes through the center of the circle, so this one is a diameter. C, BD. Again, can't be a secant because I still don't have arrows on that symbol above my B and my D. So let's go ahead and find B. B's on the circle. D's on the circle. So it can't be a tangent because that has to be outside of a circle. B to D is not going through the center. Can't be a radius, so it's got to be a chord. D, AE. Okay, so A is outside of the circle. Woohoo! So that means it can't be a radius, it can't be a chord, it can't be a diameter. Let's check on secant or a tangent. E is outside the circle. And this was really bad on my part of creating this diagram. It kind of does look like it intersects, but it's not supposed to go through. Let's pretend that it just touches at E. So that would be a tangent, because the whole entire line is on the outside of it and it just touches at one point. Even though it does kind of look like it intersects a few times right there. But that was a bad diagram making on my part. Okay, so now let's talk about tangent circles. Tangent circles are coplanar circles. So that means circles that are both on the same plane. Coplanar circles that intersect in one point. Concentric circles are coplanar circles that have a common center. So maybe we should make some pictures of these. Let's go back. So tangent circles. So tangent circles that intersect at one point. Maybe something like that. Right, they're intersecting right there in the middle. Concentric circles is like a circle inside of a circle. They both have the same center, so kind of like a bullseye. That's a bunch of concentric circles. A common tangent is a line, or it could be a ray, or it could be a segment that is tangent to two coplanar circles. So if I have two circles in the same plane, the common tangent is a line that touches both circles at one point. Or if I had tangent circles, then these would be, that'd be a common tangent. You could also get a common tangent straight down the middle. Over here, you could get a common tangent kind of going like that on diagonals too, right? So a common tangent is just a line that touches two circles at one point. Okay. All right, so here's some examples. So tell how many common tangents the circles have. So here we have two overlapping circles. So I have a common tangent. I'm going to try to, oops, didn't really hit it there, but I'm going to pretend I did. I have a common tangent there, and I can do a common tangent over here. So I would have two common tangents. For this one, we have the two outsides, so 1, 2, but then we're going to get 2 that go through the interior. So 2 internal common tangents, 1, 2. So we have a total of 4 common tangents. And then for the last one, we have, I think this is the last one, we have 2 external, 1, 2, and then you have 1 internal. It goes straight through the center. So here we would have 3. If you had concentric circles like this, then you would have none, because there's no way to get a tangent to both of those. Just, you might want to put that in your notes. Just hold on to it. Okay, so now we have a bunch of theorems that get applied to this lesson. So theorem 10.1 says, in a plane, a line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at its endpoints on the circle. So go ahead and make that diagram. So notice we have circle Q, because Q is in the center. The red line from Q to P is the radius. And if that radius is perpendicular, because that little square in there, to a line that's outside, then that has to be a tangent line. All right, so that's how we determine whether a line is tangent or not, if it is perpendicular to the radius. So we've got right triangles coming back into our life. So in the diagram, it says AB is the radius of circle A. And the question is BC tangent to circle A? So if it was tangent, this would need to be a right angle, which means this would need to be a right triangle. Well, how do we determine whether it's a right triangle? So we need to check if we have a right triangle. How do we check? We'll use the converse of the Pythagorean theorem. Does your a squared plus b squared equal c squared? So does a squared plus b squared equal c squared is the question. What should your c squared be? Well, your c squared should be the hypotenuse of the right triangle. So if that was a right angle, then my hypotenuse here would be 67. So I'm going to do 25 for my A. I'm going to do 60 for my B. I'm going to do 67 for my C. So now on my calculator, I'm going to type in 25 squared plus 60 squared, and I'm going to get a number of 4,225. And I'm going to do 67 squared, and I get 4,489. They are not equal. So this is not a right triangle. So BD is not tangent. Would be our answer. Okay, do you see how that works? So it means it's not tangent, which means it's not a right angle. So it would then intersect somewhere else on that circle. Example 2. In the diagram, S is a point of tangency. Find the radius of R of the circle. You know what? I just made a decision. We're going to skip that example. We're going to keep our life easy here at the second quarter. All right, so theorem 10.2. Tangent segments from a common external point that will be congruent. So if you have tangent segments, so here I have this tangent segment, here I have this tangent segment. If they meet at a point, a common point outside, then these must be congruent to each other. So RS's length would be the same as TS's length. So that's some easy math. So in circle C here, we're told that DA is tangent and DB is tangent, which means this would have to be the same as that. So solving for x, set them equal. 25 equals 6x minus 8. Adding 8 gets us, what, 33 is equal to 6x. Divide by 6 gets us 5.5 is equal to x. All right, and that concludes your notes.